So, we will be starting the first class of transport processes 1. So, in this course what we will be doing, we will be looking into various underlying principles of various transport processes like momentum transport, mass transport and heat transport either through a tube or through any flow channel, okay, which will be very necessary for various chemical industry, chemical engineering processes. Like you go to any sector like oil sector, you would like to transport oil from station 1 to station 2, okay, and you would like to find out what will be the flow rate, what will be the temperature, because the temperature is a crucial factor in transportation of the oil, because the oil should not be frozen or its temperature should not go beyond the flash point, otherwise there will be an explosion. Okay. So, you would like to monitor various all these dependent variables, namely temperature, concentration and flow rate of the fluid that is flowing through the tube or a pipe or whatever the material or conduit you are considering. Now, the textbooks that will be strictly following, one will be Fox and McDonald, there are several books, copies of this book available in the library, in our departmental library as well as the central library. Som and Biswas, Gupta and Gupta. These three are typical textbooks you can follow, and there are a host of books available in fluid mechanics and transport processes. Those are available. So, in the library, so any one of them can be looked into. Now, the grading will be your mid-sem exam will be out of 30 marks. Your final exam will be out of 50 marks, means whatever it will be converted out of 30 and out of 50, and there will be tests 20 marks. There is no marks for the attendance, that the teacher's impression or whatever, that will be clubbed into tests. So, it will be the grading will be purely on your performance, okay. And the exams are open book, and closed notes, okay. And this there will be number of, if you miss some of the tests, there will be there may be makeup tests depending on the validity of the absence, and these tests will be best 2 out of 3 or 4. Okay. Suppose you take 3 tests, so these 20 marks will be evaluated out of best 2. Okay. So, that will be the grading pattern. Now, let us have some introduction of this course. Now, we will be looking into basically various kinds of flows, and we will try to visualize the flow. The flow in general may be a fluid. Definition of what is the definition of fluid? A definition of fluid is a material that flows, okay. And the flows will be considering mainly of 2 types. One is bounded flow. The example is flow through a conduit. Now, this conduit may be having circular cross section, then it is a pipe. It may be having a rectangular cross section, then it is a channel flow. It may be having a triangular cross section or whatever. And second one is unbounded flow. It is sometimes known as free surface flow. That means, there is, it is not flow through a conduit, there is a solid wall, flow is occurring over that, the other end is open to atmosphere. Okay. This surface is free, it is not bound. So, it is called a free surface flow. Now, what is flow characterization? We will be looking into point variation of some dependent variable inside the flow domain. like let us say velocity components. It is basically determination of velocity components in terms of as a function of x, y, z, t or r, theta, z, t, either in the rectangular coordinate or in the radial polar coordinate, whatever you are having. And if so, there will be three components of the velocity, right? X component, y component and z component as a function of space and time. If you know completely, then the flow behavior in the flow domain is completely established. Determination of temperature profile. As a function of space and time. Determination of concentration profile. As a function of space and time. So, flow characterization means determinations of velocity components, the temperature profile, the concentration profile of various species present in your system as a function of space and time. Once all these quantities are known to you, you can characterize or visualize a flow. Now, suppose you determine all these quantities, what is the outcome? What will you be doing with these determined quantities? The outcomes are, you can compute cross sectional average velocity. Suppose a steady state flow is occurring and you know velocity is a function of x, y, z. So, you can carry out a computation by doing a to calculate the average velocity, which is basically the average over the cross section. Why this is required? You can measure this value. So, you connect all your computed variables to the measurable quantities, like there is an instrument called Rota Meter, you must be knowing about it. What Rota Meter does? The Rota Meter is placed in the flow line and it measures the flow rate. Okay. Since the flow rate is measured, you know the area of the cross section of your flow channel. Okay. You divide that by the cross sectional that cross sectional area, you will be getting the average velocity. So, all these quantities that you are computing or calculating should be compared against the measurable values. Like all the velocity components that you are calculating, that should be, you should make a cross sectional, you should calculate the cross sectional average velocity to calculate the cross sectional average velocity. Okay. Because it is measurable quantity. Why to do that? You can determine whether the flow is laminar or turbulent. This is directly connected to determination of flow regime. Laminar, turbulent or transient. There is a dimensionless number called Reynolds number. It is defined as rho v d by mu. D is basically equivalent diameter. DE is equal to pipe diameter if it is a flow through a pipe. It is equivalent diameter for other channels and defined as 4 into weighted area divided by weighted perimeter. Okay. D is basically diameter if it is a pipe. If it is not the circular cross section, it will be calculated using this formula. Okay. Suppose you are having a rectangular cross section with W is the width and H is the height. What is D equivalent? D equivalent will be nothing but 4 times weighted area. What is the weighted area? width times height. What is the weighted perimeter? Right. Now, if h is very small compared to width, if it is a thin channel, then you can neglect h in the denominator and this w will be simply cancelled out and it will be twice of h. Okay. If it is a very thin channel. Okay. Now, rho is the density of the fluid, mu is the viscosity of the fluid, v is the cross sectional average velocity. Okay. Once either you measure the cross sectional average velocity or calculate the cross sectional average velocity, calculate the Reynolds number, that is important. If Reynolds number is less than 2200, then it is called a laminar flow. If it is greater than 4000, it is called a turbulent flow. If it is in between, it is called a transient flow. So, from the cross sectional average velocity, you can find out what is the Reynolds number you are having in your flow domain and what is the flow mechanism, flow regime, whether it is a laminar or a turbulent flow or a transient flow. The second quantity that you can calculate is the shear force at the wall. Okay, the shear force at the wall, that means if there is a flow over a plate or over a tube or whatever the system you are having, that will be the fluid flowing over the wall will be giving a force, giving rise to a force. Okay. So, you have to apply an equal force from outside to keep that material over which the flow is occurring in place. Okay. That shear force can be calculated from the cross sectional average velocity. The third quantity you will be calculating is the pressure drop. From all these velocity components etc., you can find out what is the pressure drop across the line. Let us say station 1 and station 2, what is the delta p over this length L. This is very important from a chemical engineering point of view. Whatever you do in any fluid, you look into any exercise of the fluid mechanics book, a typical fluid mechanics book, you will be asked to calculate what is the pressure drop across this length. You do a heat exchanger calculation. One of the design aspect is calculation of the pressure drop. A pump is forcing a fluid to flow from station 1 to station 2. What is the pressure drop? Why the pressure drop is important? The pressure drop is important because the flow is occurring because of that pressure drop, and upstream pressure is always greater than the downstream pressure. So, that the flow will be occurring in the forward direction from 1 to 2. Now, estimation of delta p is very important because it directly is related to the rating of the pump. What is the power of the pump that you will be requiring, maybe you will be designing for your plant. So, you have to give them that if this much amount of flow is occurring of this tube of length so and so and diameter of some specific diameter. So, probably you have to calculate what is the delta p, and then you can, that is directly related to the rating of the pump. So, you can tell them that I require 1 horsepower pump to materialize this type of operation. Okay. Whenever you will be transporting a liquid, you require a pump. Whenever you will be transporting a gas, you will be requiring a compressor. So, whatever the fluid may be, you require the pressure drop calculation. Okay, that is very important. The fourth one is prediction of temperature field. And from that you calculate the cross sectional average temperature. Temperature field means temperature is a function of x, y, z and t. Now, you do a cross sectional averaging and get the average temperature. This is measurable. You just insert a thermometer or thermocouple, that will not give you a point value of temperature, that will give you an average value of temperature. you calculate the concentration field as a function of space and time and do a cross sectional averaging, and if you take out a sample from any point of the pipeline and give that analysis in the laboratory, that will give you the basically average concentration. So, again the cross sectional average concentration is important, and you can compare your calculation with the these measured values and can come to a conclusion whether your calculation is correct or not. Why these calculations you are requiring? Because you will be giving whenever you will be joining a company or doing some R&D activities, probably you will be giving a target that this much amount of flow rate or this much amount of product liter per day I would like to have. Okay. Now, you have to probably giving a design, what will be the length, what will be the diameter, what will be the pressure drop, what will be the rating of the pump. Now, you do certain experiments, and you can conducting experiments, you can say okay, these will be the specifications, so that you will be meeting your target. Now, your business will be growing up, and after 6 months you would like to scale up your plant. So, again you will be doing a same type of experiments. No, you should not, because conducting of experiments require involvement of manpower, involving the cost of raw material, cost of the equipment. Okay. So, you do a model calculation and predict on a very small scale what will be the performance. If that matches with the experimental results, you can just scale up your feed components, or concentration, or chamber of volume of the reactor, etc., and get your predictions. So, by doing these calculations, number one, you will be reducing the number of experiments that you will be conducting to verify a particular target. Secondly, by doing this simulation, you will be reducing your manpower involvement, cost involvement of raw material, or daily labor, whatever. Okay. So, that is why these calculations are very important. These cross sectional average temperature and cross sectional average concentration, they have typical names. They are known as the cup mixing concentration or cup mixing temperature. Okay. Let us look into the various physical properties, those will be involved in such calculations. Density, that will be required, density of the fluid, viscosity of the fluid, specific heat, thermal conductivity, diffusivity. Okay. These properties are typically involved in all of the transport calculations, and these are also known as the transport properties. Now, let us look into in such calculations what are the equations, gross equations they are involved, or gross equations need to be solved. The first equation that you are going to write is overall material balance. In its differential form, all these equations are partial differential equations. The overall mass balance or material balance is basically also known as equation of continuity. Okay. The second group of equations that you are going to write down is momentum balance equation. Now, in momentum balance equations, you will be getting 3 momentum balance equation. One is in x direction momentum balance, second one is y direction momentum balance, third one is z direction momentum balance. Now, all these equations will be involving Vx, Vy, Vz and pressure. Okay. Vx is velocity component in the x direction, y direction and z direction, and pressure variation as a function of x, y and z. These equations are also known as the equations of motion. And they are also known as Navier-Stokes equation. So, you will be writing one overall mass balance and you will be writing 3 overall momentum balance equations in their differential form. The third equation that you are going to write is overall energy balance. From this, what you will be getting? You will be getting the temperature profile as a function of x, y, z and t in general. Okay. This overall energy balance involves the velocity terms as well as the conductive terms, that means convective terms as well as the conductive terms. So, these will be coupled with the momentum balance equations. Suppose you are having a reactive system, okay. Two components, two reactants are reacting and giving rise to one product or two products or whatever products. Let us say n number of species are involved, n components are involved. So, you will be writing n minus 1 component balance equation, species balance or component balance equation. Why n minus 1? You will be leaving behind one or last one component at least that will be calculated from overall material balance. Overall material balance has to be used to find out concentration of species, let us say nth component. For n minus 1 components, you will be writing the component balance equation and the last one will be found out from the overall material balance. If you write down the component balance equation for the nth component, you will be finding out that overall material balance may not be matching. Then that will be a typical problem, that will be a very serious problem. You are doing a calculation, doing a simulation between 2 points through a pipeline where a reactive system is going on, let us say polymer reaction is going on and you know how much monomer has been fed per unit time. Same amount of product should be out at any cross section at the exit of the pipeline or the reactor. Okay. So, the matching of total material balance is very crucial. Right? Recently we were doing a project of Gas Authority India Limited. They are having some polymer reaction going on in their reactor system. We have to simulate the reactor system. Okay. So, we found out that whenever we were writing all the component balance, that overall material balance is not matched. It always happens. So, you leave behind only one component, do n minus 1 component balance and the last one will be calculated from the overall material balance by subtracting. Okay. So, equations number 1 and 2, from that you will be getting the velocity components. And pressure distribution, velocity distribution and pressure distribution. That means, you will be getting Vx, Vy, Vz and P as a function of x, y, z and t. There are 4 unknowns and 4 equations. There are 3 equations in momentum balance, 1 equation in equation of continuity. So, 4 equations, 4 unknown, solvable system. Okay. Now, typically these equations are coupled partial differential equations. Okay. Under certain simplistic situation, you can simplify this equation and omit some of the terms. typical example is, suppose there is a flow through a thin channel. Okay. The z component is pretty long. If z component is pretty long, all the derivative with respect to z will be very small. So, you can neglect those terms which will be occurring as del z, they will be negligibly small compared to the other terms. So, under certain simplification or simplistic conditions, the various terms in equation of motion will be omitted and the whole equation can be simplified. From 2 and 3, you will be getting the temperature profile. From 2 and 4, you will be getting the concentration profiles of various species. These are coupled equations. Under certain situations, they can be decoupled. Can be decoupled. Now, we have discussed about several the equations. We have in fact, we have covered all the equations that you require to solve in this course or any transport processes. Now, specifying an equation to solve a particular problem is not enough. What you require? The complementary is that you must be having certain boundary conditions. Without boundary and initial conditions, you cannot solve a differential equation. Now, let us look into typical boundary conditions that will be appearing in fluid mechanics problem. Now, 6 types of boundary conditions can generally occur. The first one is solid surface. The condition on the solid surface must be specified, and this solid surface can be porous like a membrane, can be impervious like a solid tube. A free liquid surface. Open channel flow or free surface flow. Liquid interface. Like flow of two immiscible fluids through a pipeline, kerosene and oil. Liquid vapor interface. Sometimes the inlet or exit conditions are specified, that will appear as the boundary condition in our problem. Okay. Suppose there is a flow through a channel and it is a reactive flow, and at this point there is an inlet condition, the concentration is specified as C naught. So, that will be one of the boundary condition. Okay. The sixth one is known as the physical boundary condition. These boundary conditions may not, all the 5 boundary conditions we have discussed here, they are specified in the problem. You know, all these boundary conditions are specified. Now, the physical boundary conditions may not be specified, they may be appearing from confirming the physics of the system. Suppose there is a flow through a tube of radius r. At r equal to capital R, the velocity, suppose a fluid is flowing with a velocity v in the x direction. The velocity component in the x direction is having a 0 velocity, because this wall is stationary. This is known as the no slip boundary condition. I will be coming to that just after this. So, this is specified, this is known as the no slip boundary condition. On the other hand, at r equal to r, and typically these equations are of second order. So, you require two boundary conditions to solve these equations. At r equal to 0 means at the central line the velocity will be finite, but you do not know the velocity. The velocity in fact it will be maximum there, it will be assuming some finite value, some non-zero value, non-zero constant value, but you do not know that value. So, so either you use V x is finite at r equal to 0, or you use del V x del r equal to 0 at r equal to 0. Okay. V x is finite means, suppose mathematically that implies that you will be having a profile something like this, let us say a 1 plus a 2 by r plus a 3 r square. Okay. The constants will be evaluated from the conditions. Now, at r equal to 0, you know the V x will be assuming some finite value, but if you put r equal to 0, this term becomes infinite, right. That means, your whole velocity component will become infinite r equal to 0, but that cannot happen. In that case, the conclusion is the corresponding constant appearing is equal to 0. That means, a 2 equal to 0, or other words you can put del V x del r equal to 0. These two are equivalent. So, this comes from the physics of the system. This is known as the physical boundary condition. Okay. Some of the examples of this boundary condition: condition at the solid surface. If you have a stationary or impervious wall, V is equal to 0. That means, V x is equal to V y is equal to V z equal to 0. If your wall is moving, it is a moving wall, let us say, moving with a constant velocity, let us say u 0 in the x direction, then V x will be u 0 at the wall. This is known as the no slip boundary condition. There is absolutely no slip between the wall and the fluid particles adjacent to the wall. That means, fluid particle will be assuming the velocity values which will be that of the wall. If the wall is stationary, then the fluid particles will be at rest at that particular point. If it is moving, it is having the same velocity. This is known as the Couette flow. The flow induced by the velocity of the motion of the wall is known as the Couette flow. Similarly, you can have constant wall temperature condition. This is known as the CWT condition. Suppose the fluid is flowing through a tube, and at r equal to capital R on the wall, the temperature you are maintaining at constant temperature. You are maintaining a constant temperature T naught at the wall of the pipe, then it is known as the constant wall temperature. Sometimes the heat flux at the wall is maintained constant, it is known as the constant flux condition. In this case, minus k del t del y del t del r at r equal to capital R is constant, let us say q 0. You are maintaining, or suppose you have put an electrical wire around this tube and passing a current which will be generating energy at constant rate. That means, you are inserting or you are you are adding constant heat flux at the wall. Okay. Sometimes the heat is extracted from the wall at a constant rate. If that is the case, it is known as the constant heat flux condition. Insulated surface. These are several examples. The surface is insulated. Okay. That means, you are not allowing any heat to go out or not allowing any heat to come into the system. That means, at the surface minus k del T del y equal to 0, y is the normal to the surface. That means, del T del y equal to 0. Okay. Cooling or heating at the wall. Suppose you are conducting an exothermic reaction in a tubular reactor and the temperature is going up. So, you would like to cool down the temperature. So, on the outside of the tubular reactor, you put a jacket, cylindrical jacket, and pass some, let us say, ice water. Okay. That means, at the what is the condition? For this physical situation, the condition will be what will be the total heat that will be coming out, that will be transported at this point. It will be convected away by the fluid outside. That means, minus k del T del R will be equal to, that will be the total amount of heat flux that is coming per unit time at the wall will be equal to amount of heat that will be convected away by the cooling liquid or coolant, H T minus T C. H is called heat transfer coefficient, and T C is the coolant temperature at R equal to R. This is known as the cooling heating condition at the wall. So, this can also appear. Okay. Permeable wall. Suppose the wall is porous like a membrane. Okay. There is a channel, you are placing a membrane at the bottom channel or bottom plate. So, the fluid will be coming out, right, if it is a porous membrane. So, what will be the condition at this surface at y equal to 0? At y equal to 0, your Vx will be equal to 0 because of the no slip condition. The wall is not moving in the x direction. So, Vx will be equal to 0, but Vy will be equal to minus V0 if V0 is the rate or permeation rate, constant permeation rate through the wall. If the wall is permeable, then this type of boundary condition you can come across. Now, in mathematical terms, so what you have seen? You have seen there are three kinds of boundary conditions can appear. One is, the first one is the dependent variable is assuming a value. For example, velocity is equal to 0, temperature is equal to T naught, like that. Second one is the derivative of dependent variable is assuming a value. Example, insulated wall, del T del y will be equal to 0. Constant heat flux condition, minus k del T del y will be equal to Q naught. Third one is the dependent variable and its derivative. These derivatives are basically normal derivative of the to the surface. the dependent variable and its derivative are connected through an algebraic equation like the cooling heating boundary condition. Okay. That minus k del T del y will be equal to h into T minus T c. So, dependent variable T and its normal derivative del T del y are connected through an algebraic equation at the surface. Now, in mathematical terms, this class of boundary conditions are known as the Dirichlet boundary condition. Okay. The second class of boundary condition where the the derivative of dependent variable assuming a value is known as the Neumann boundary condition. The third one where the dependent variable and its derivative are connected through an algebraic equation is known as the mixed boundary condition or Robin mixed boundary condition. Okay. The second type of conditions that we have talked about, that liquid liquid or solid liquid, liquid liquid or liquid vapor interface. Okay. Suppose you are having a flow of two immiscible liquids through a tube or a channel like kerosene and water. So, what will be the interface boundary condition? At the interface, there will be continuity of velocity, means velocity of phase 1 will be equal to velocity of phase 2. There will be continuity of temperature of the two phases at the interface. There will be velocity of the shear force at the interface. This means tau 1 equal to tau 2, or in other words, this is in terms of velocity profile, this is known as mu 1 del V 1 del y is equal to mu 2 del V 2 del y. Okay. Now, if it is a liquid vapor interface, this boundary condition will be, suppose 1 is vapor and 2 is liquid. Now, if it is let us say air water interface, air will be having a viscosity around 10 to the minus 5 Pascal second, and water will be having a viscosity 10 to the minus 3 Pascal second. So, typically the vapor viscosity is at least 2 or 3 order of magnitude less than the liquid viscosity. So, in that case mu 1 will be very small compared to mu 2. So, for a vapor liquid interface, del V 2 del y will be equal to 0, because simply because of the fact that mu 1 is order of magnitude less compared to mu 2. Okay. Inlet and outlet condition, those will be specified. As I said, suppose some fluid is coming into a through coming into the pipeline or whatever, at the inlet the temperature will be specified, the concentration will be specified, so on and so forth. The pressure will be specified. Then the last one is the physical boundary condition. As I said, for the flow through a pipe at r equal to 0, the boundary condition will be del V del r will be equal to 0, del V x del r equal to 0 if it is x direction or V x is finite. Another example is, suppose there is a stationary, suppose there is a wall, a plate is placed in a stationary fluid, and at time t equal to 0, it starts moving in the x direction with a constant velocity u 0. In that case, what happens? The fluid particles closest to the very adjacent to the wall will be having a velocity u 0, because of the viscosity, the resistance against the flow will be occurring, and as you go up normally from the surface, the fluid particle will be having less velocity, and at some distance, let us say y equal to delta, the fluid particle will be again at rest. That means, at y equal to delta, the fluid particle will not recognize the existence of this moving plate. So, what will be the typical boundary condition? Typically, boundary condition will be at y equal to delta, Vx is equal to 0. At y equal to 0, Vx equal to u0. Now, again this delta is unknown to you. For the ease of mathematical treatment, this is replaced by infinity, because it has to happen at infinite distance from the plate, the fluid particle will be at rest. So, for the ease of mathematical treatment, it is replaced by y equal to infinity, Vx equal to 0. Okay. So, this is another example of a physical boundary condition. Okay, the frame of reference. Now, two types of frames of references that will be those are generally used for this type of fluid mechanics calculations. One will be the Lagrangian frame of reference, it is also known as the moving frame of reference. Second one is Eulerian frame of reference or stationary or fixed frame of reference. Now, with Lagrangian frame of reference, you will be tracking up all the fluid particles. Now, there will be n number, since it is moving frame of reference, the observer is sitting on a fluid particle and tracking its motion. That will be very difficult, right? And not only that, for the if you use the Lagrangian frame of reference, you have to write down infinite number of equations characterizing infinite number of particles in a control volume. That will be a that will be a heavy task or computation. So, generally Eulerian frame of reference is used or stationary frame of reference is used all these fluid mechanics calculations. Okay. So, anyway, we will be continuing these things in the next class, and we will be deriving the equation of continuity. Okay. Thank you.
Good morning and welcome to another semester at IIT Kharagpur. In this course, what we are going to study is different transport processes. So, I will tell you more in detail what transport processes are, what could be its applications, the governing equations, fundamental concepts, etc. But before that, let me formally tell you that this course, being a video lecture, has certain restrictions in terms of student-teacher interaction. I would like to minimize that that restriction in the sense that you are free to stop me anytime and ask me any questions that you want. This I would always encourage, that is interaction or questions from you. This course is organized in such a way that 2 lectures will be taken by me and 2 by Professor Este. He is going to deal mostly with the fluid mechanics part of the course, and I would try to give you an unified approach of different transfer processes. All the exams except class test would be open book, closed notes. The books that we are going to follow, the first one is the text, it is Bird, Stewart and Lightfoot. The title of the book is Transport Phenomena. So, this is going to be the text for this course. And the other books which you would need and have to refer to from time to time, one is by Incropera and DeWitt, it is Fundamental of Heat and Mass Transfer. The second one is by Holman, Heat Transfer, and the third is Treble, Mass Transfer. The weightage for different components of this course are class test 20, mid semester 30 and end semester 50. You have any question about this? So, I suppose the ground rules are clear from the beginning, that the textbook, what are the textbooks, the percentage of marks in different components and the type of exams that we are going to have. Okay. With this, I think we are in a position now to start our study of transport processes. Now, first of all, what is transport process? What's its importance in terms of engineering? and this specific subject is important in different branches of engineering, starting with chemical, biotechnology, mechanical engineering, control of any chemical process in which the instrumentation engineers can play a very important role. So unless and until you know the fundamental physics behind all these processes, it would be very difficult to design a process, develop a new method, or develop a control strategy for some processes. Suppose you would like to, you are in an industry, and in most of the cases the work there involve production of something, add value to certain raw materials. Now how you are going to heat a liquid? Now what is going to happen when a solid block is heated? You bring the two liquid together, mix them in a vessel, in a specially designed vessel, and let's say the outer wall of the vessel is wrapped with some kind of an electrical heating. Now fine, so the liquid very close to the wall is going to be heated, but how you are going to transport the heat to the center of the vessel? You want an uniform temperature. So conduction of heat, convection of heat, and in some cases radiation, all three are going to play a very important role in many process industries. Or suppose you are carrying steam through a pipe, you would like to insulate the pipe in such a way that no steam condenses in the pipe, such that you get maximum energy at the point where you want it to be. So how do you insulate it? What's going to be the heat transfer? Because no insulation is perfect. There is always going to be some amount of loss through those insulations. So how you design the insulation? What would be, if you know certain properties of the material, namely thermal conductivity, which you already know, how do you design a material of low thermal conductivity in some cases, very high thermal conductivity in other cases, and the equations that govern flow of heat through solid, through liquid, and through gases. Because as process engineers, you have to maintain certain temperature conditions inside your plant such that the reaction that you want can take place properly. So the study of heat transfer, that's also again a transport process, is intimately connected with with any process engineer, with any engineer, and that's going to be our second topic in transport process 1. And finally, when the things are brought together, the temperature is correct, then the reaction is going to start. So whenever the reaction is going to take place, now the reaction can be different types. It could be a homogeneous reaction in which the reaction takes place everywhere in the medium, or it could be a heterogeneous reaction, in which case, let's say you are adding catalyst particles. So reaction is only taking place on the catalyst surface and nowhere else. These are the two main types of reactions, homogeneous and heterogeneous reactions, that are mainly that are the most common ones. Or maybe it's a solid liquid reaction. The liquid is come to the surface of the solid, react, some product is formed, and the product has to go back to the main stream such that you can separate it from the reactants. It's not sufficient to produce a material which you want. You also have to separate it from the reactants. I have one layer of liquid which is it's very close to a solid surface. So the solid surface is stationary. If the solid surface is stationary, then the liquid layer which is clinging to this solid surface would also be stationary. Everything is supposed stationary at one, and you have certain depth of the liquid over the solid surface. At some point of time, you have started to move the solid plate with a constant velocity in the x direction. So pictorially it would look something like this: a solid plate and a liquid layer on top of it. The solid layer moves with a velocity, some velocity in the x direction, and as a result of which, what's going to happen? The liquid layer would also start to move in this direction. Had this liquid if I replace this liquid with a solid, what is going to be the velocity of the solid? Equal to that of V. But since it is liquid, the layers one on top of other will not move with the same velocity. There would be definitely a gradient in velocity. Okay. The layer of fluid which is very close to the solid surface would move with a velocity equal to V, but as I move away from another point, this layer would move at a velocity less than V. So, as I progressively move in the y direction, my velocity would decrease. Now, what is the other effect of this? What is going to happen is the molecules which are moving at a faster velocity compared to the layer just above it, some molecule will travel to this one, and as a result impart some momentum, impart some higher momentum on this slower moving fluid. Is it clear? A layer of fluid which is moving with 5 meter per second, and this layer, let us say it is moving with 2 meter per second. So, molecules when they travel from here to there, they will take with them higher momentum which they would transfer to the layer which is moving at a slower speed, as a result of which this layer will also try to move faster. But since whenever you are talking about this transfer, there would be some sort of a resistance. So, these two layers can never move with the same velocity. Okay. This velocity would always be lower than the velocity of a plate, velocity of a layer of liquid lower than it. Now, as you can see, so I have some sort of a transfer taking place here as well. This transfer is nothing but momentum transfer. So, momentum transfer is the effect. Whenever you think of motion of a fluid, whenever there is a difference in velocity in different layers of the fluid, what you have is transfer of momentum from one layer, from faster layer to the slower layer. So, the effect of this difference in velocity is momentum transfer. And what is the cause of this? Velocity gradient. So, it is not the absolute value of velocity, it is a difference in is the distance between the two layers.